Hello, my name is Santiago Cortes. I'll be presenting our system called PIVO, which stands for Probabilistic Inertial-Visual Odometry for Occlusion-Robust navigation. I'll start by stating the problem. We want to navigate a device through an environment using the camera and the IMU. The devices available in most smartphones, which is our goal, are very, very bad for this particular task. The camera has a narrow field of view, which means that features in natural motion won't stay in the frame for long. And then the IMU has a lot of annoying biases and very noisy measurements. So the idea is to make a system that will take the best out of each of the modalities and combine them in such a way to have what we call robust odometry. This is odometry. We are not closing loops or doing localization per se. Our system takes into account all the cross covariances. So we are propagating the uncertainty of all the measurements through not only the dynamics, but the geometry and the minimization problems, which means we have a much closer grasp on the uncertainties of the estimation. We claim that this will make our system robust to full occlusion of the camera, dynamic objects, sharp turns, and these sort of like bad cases for odometry. Very fast, I'll talk about the model. The model dynamics are driven by the IMU. The inference is done in an extended Kannala filter, and then the visual update, which is the most novel part in our work, is we implicitly integrate and do the update for the visual odometry part by propagating the uncertainties of the poses into the localization of the feature itself, and then integrating it out to do the update. You can see here that we're comparing to a very popular algorithm, and well, it doesn't show very well, but I can tell you, we have a tighter fit of the true distribution, which is black. It's a Monte Carlo simulation, and the big one is the popular method. So this is how it looks. We start in an office space, walking around, no particular, very natural motion. We go down a flight of stairs. You can see that the motion is properly, it looks correct on the side, and then the total path also matches the map, which you can see down here. We are in the city center. There is people walking. This is this is Finland crowded. Yeah, we go back indoors, we go down some stairs, and it's able to keep not only local motion, but the correctness of the track with respect to itself. So we propose a principled approach for fusing visual and inertial information. We prove and claim to be robust to occlusion and dynamic objects in the scene. In ideal cases, which are wide-angle cameras and very high-quality IMUs, we are comparable with most of the work done out there, but I think we really shine when we compare with, when we put in really, really hard cases like this one. Okay, so if you want any more details or videos, this is my poster. Thank you.